January 1952, Sherman Hill, Wyoming. A Union Pacific locomotive just pulled 6,000 tons up a 15% grade at speeds diesel engines couldn't dream of achieving. The crew was euphoric. Management was terrified. Why would a railroad company fear the most powerful locomotive ever built? The engineering calculations spread across Otto Jabelmann's desk at Union Pacific headquarters in Omaha told a story that every American railroad executive understood but refused to accept. Spring 1948. The diesel-electric revolution that had transformed American railroading was hitting a mathematical wall nobody had anticipated. Jabelmann, chief of motive power, stared at performance reports from Sherman Hill, the brutal 1.55% grade climbing out of Cheyenne toward the Continental Divide. The numbers revealed diesel technology's fundamental limitation. A single diesel-electric locomotive generated 1,500 horsepower. Moving Union Pacific's standard 4,000-ton freight up Sherman Hill required 3 diesel units, working together, consuming 3 crews' wages, 3 maintenance schedules, and 3 complete propulsion systems to accomplish what steam locomotives had done with brutal inefficiency but singular power. If you want to see more videos about old trains, make sure to subscribe so you never miss another video. The war years had proven diesel superiority over steam in fuel economy and maintenance costs. But the post-war freight boom exposed a problem that diesel manufacturers hadn't solved: mountains. The Rocky Mountain corridor that carried western freight to eastern markets created grades that defeated diesel efficiency. Running multiple diesel units in tandem provided power but destroyed the economic advantages that justified the technology switch. Union Pacific's traffic department projected freight volumes that would double within 5 years as American manufacturing expanded westward. The Denver to Omaha corridor alone required 147 locomotives daily to maintain schedule reliability. Each additional diesel unit added $125,000 in capital costs, $47,000 annually in maintenance, and operational complexity that multiplied with every locomotive coupled together. European railroads face similar mountain challenges but relied on electrification systems that American railroads considered economically impossible across the vast distances of western terrain. Overhead wire electrification cost $87,000 per mile of track. Union Pacific's transcontinental route stretched 1,911 miles through territory where electrical infrastructure barely existed. The $166 million investment would bankrupt the company before the first wire energized. Jabelmann's predecessor had commissioned studies from every diesel manufacturer in America seeking solutions to the horsepower problem. General Motors' Electromotive Division offered 8-unit diesel units that would generate 12,000 horsepower but require coordination systems that introduced catastrophic failure points. American Locomotive Company proposed double diesel designs that increased individual unit power to 2,400 horsepower, but doubled fuel consumption per ton-mile hauled. The fundamental physics defeated every proposal. Diesel-electric locomotives converted fuel to mechanical power through compression-ignition engines driving electrical generators. The diesel engine's thermal efficiency topped out at 38% under optimal conditions. Achieving significantly more power meant significantly larger engines, which meant heavier locomotives, which meant reduced hauling capacity, which negated the entire purpose of increased power. Beyond his office windows, Union Pacific's diesel fleet represented $47 million in rolling stock that would become obsolete if freight volumes exceeded diesel capability. The railroad couldn't afford to return to steam's inefficiency, couldn't afford European-style electrification, and couldn't push diesel technology beyond its thermodynamic limits. American railroading needed a power source that didn't exist in commercial transportation. The answer would come from an industry that had nothing to do with trains. The breakthrough arrived through General Electric's Aviation Division in Lynn, Massachusetts, where engineers working on jet engine contracts for the Air Force understood power generation principles that railroad designers had never considered. Frank Knopfsinger, GE's chief mechanical engineer for transportation, reviewed turbine technology reports that revealed possibilities diesel engines could never achieve. Gas turbines operated on fundamentally different thermodynamic principles than piston engines. Instead of compression ignition in individual cylinders, turbines burned fuel in continuous combustion chambers that spun turbine wheels at 20,000 RPM. The technology delivered staggering power-to-weight ratios that made jet aircraft possible. A single turbine engine generating 4,500 horsepower weighed 15,000 pounds. An equivalent diesel power plant weighed 87,000 pounds and required 3 times the physical space. The aviation industry had perfected turbines. Reliability through military necessity during World War II. British jet fighters and American B-45 bombers proved that turbine engines could operate continuously under conditions that destroyed piston engines within hours. Fuel consumption remained higher than diesel operation, but turbines ran on cheaper residual fuel oils that diesel engines couldn't burn without extensive refining. Knopfsinger approached Union Pacific in November 1948 with a proposal that challenged every assumption about locomotive design. Build a gas turbine electric locomotive that would generate 4,500 horsepower from a single power unit, 3 times the output of contemporary diesel designs. The turbine would drive an electrical generator using the same proven electric traction motors that diesels employed, combining jet engine power with railroad electrical systems. The engineering advantages extended beyond raw horsepower. Turbine engines had 8% fewer moving parts than diesel engines, eliminating the complex valve trains, fuel injection systems, and cooling requirements that made diesel maintenance expensive. Continuous combustion created smoother power delivery without the vibration and shock loading that diesel pistons generated. The turbine's compact size allowed designers to package 4,500 horsepower in a locomotive frame only slightly larger than standard diesel units. Union Pacific's board of directors reviewed GE's proposal with skepticism born from decades of locomotive experimentation that promised revolution but delivered disappointment. The railroad's engineering department had evaluated steam turbines in the 1930s, finding them mechanically sound but operationally impractical. Gas turbines represented unproven technology in railroad service where reliability determined profitability. Jobelman convinced skeptical board members to authorize one experimental locomotive. The $350,000 development cost exceeded diesel unit pricing by 4%, but the potential payoff justified the risk. A successful 4,500 horsepower single unit could replace 3 diesel locomotives on Sherman Hill service, eliminating 2 crew salaries, reducing maintenance schedules by 66%, and simplifying operational logistics that multiplied costs across Union Pacific's entire Western territory. General Electric began construction in January 1949 at their Erie, Pennsylvania. Locomotive Works. The design married jet engine technology with railroad electrical systems that had evolved through 15 years of diesel-electric operation. The turbine power section came directly from military jet engine designs proven reliable in B-36 bomber service. The electrical transmission system used standard components that Union Pacific's maintenance forces already understood. The prototype emerged 18 months later carrying designation number 50, the first gas turbine electric locomotive built for commercial railroad service in American history, the machine that would either revolutionize Western railroading or prove that jet engine technology belonged in the sky. January 17, 1952, 4:30 a.m., Cheyenne Depot Yard. Engineer Bill Withen walked around Locomotive 50 with the methodical inspection routine developed through 23 years of steam and diesel operation. But nothing in his experience prepared him for the machine GE had delivered. The turbine locomotive stretched 83 feet long, resembling a standard diesel cab unit, but emitting a high-pitched whine that sounded nothing like diesel rumble or steam hiss. The turbine section sat behind the cab, enclosed in streamlined cowling that concealed the jet engine spinning at idle speed. No visible exhaust stack, no rhythmic pounding, no mechanical vibration transmitted through the frame. The machine felt alien despite its familiar electrical control systems. Dispatcher orders assigned 50 to the eastbound manifest freight that would test every capability GE claimed. 127 loaded freight cars totaling 6,200 tons, bound for North Platte across Sherman Hill's maximum grade. The consist included 40 refrigerator cars carrying California produce, 35 boxcars loaded with lumber from Oregon mills, 28 flat cars hauling military vehicles to Omaha, and 24 tank cars filled with crude oil from Wyoming fields. Standard diesel practice required three 1,500 horsepower units to move this train reliably. Locomotive 50 would pull it alone. The departure proved the turbine's first surprise. Within advancing the throttle through 8 positions, feeling electrical traction motors respond with smooth acceleration that builds speed without the jerking transitions that multiple diesel units created. The turbine's continuous power delivery eliminated the synchronized loading problems that plagued diesel consists. By milepost 3, the train was rolling at 23 miles per hour with the throttle still at position 6. Sherman Hill began at milepost 516, climbing 2,057 feet over 32 miles of 1.55% grade that tested locomotive capability against gravitational physics. Within watched the speedometer as the grade steepened, waiting for the inevitable slowdown that diesel operation accepted as mechanical reality. The turbine maintained 19 miles per hour at position 8, with the ammeter showing 75% generator capacity remaining. The machine was pulling 6,200 tons uphill faster than 3 diesels managed with lighter components. The sound was unlike anything railroad operation produced. The turbine's jet engine whine rose and fell with throttle position, creating a sensation of continuous power that steam locomotives achieve through different mechanical means. No cylinder beats, no exhaust chuffs, no diesel engine roar. The cab vibration measured imperceptibly compared to diesel operation that fatigued crews through hours of mechanical pounding. At milepost 543, the summit of Sherman Hill, fireman Tom Peterson recorded statistics that would circulate through Union Pacific's operating department within hours. The 6,200-ton train crested the grade 14 minutes faster than 3 diesel operation with identical consists. Fuel consumption measured higher per gallon but lower per ton mile because the single turbine eliminated the inefficiency of multiple diesel prime movers. Most remarkably, the locomotive showed no signs of thermal stress, bearing temperature or mechanical strain that limited diesel performance on sustained grades. Within brought the train into Laramie 47 minutes ahead of schedule. The crew's enthusiastic report reached Omaha before the train departed for North Platte. Word spread through Union Pacific's engineering department that GE had delivered performance exceeding every specification promised. The turbine locomotive worked flawlessly. Management's problems were just beginning. By March 1952, Locomotive 50 had accumulated 12,000 miles of mountain service, while Union Pacific's maintenance department discovered consequences that GE's development team hadn't anticipated. Chief Mechanical Officer Harold Anderson reviewed damage reports from Cheyenne shops that revealed problems nobody considered during experimental design. The turbine's 4,500 horsepower output created rail stress patterns that exceeded design specifications for track structure built to handle 1,500 horsepower diesel units. Anderson's track engineers measured rail deflection under turbine operation at 0.34 inches. Compared to 0.18 inches under equivalent diesel consists. The difference seemed minor until multiplied across thousands of miles of daily operation. Rail metallurgy developed for diesel service couldn't withstand the concentrated power delivery that turbines generated through 6 driving axles. Track inspection crews reported rail head wear patterns appearing after 8 months that normally took 3 years to develop under diesel operation. The 132-pound rail section standard on Union Pacific's main line could handle turbine forces but required replacement schedules that doubled maintenance costs per mile. Bridge engineering presented even grimmer calculations. Union Pacific's western corridor crossed 2,347 steel bridges designed for steam locomotive loadings. Diesel operation had reduced dynamic forces on bridge structures, allowing maintenance deferral that saved millions annually. Turbine locomotives reversed this advantage. The higher power concentration created harmonic vibrations in bridge spans that civil engineers measured with accelerometers borrowed from earthquake monitoring equipment. The Green River Bridge, a steel through truss structure built in 1917, showed stress readings under turbine operation that approached World War I-era steam locomotive levels despite the turbine unit weighing 40,000 pounds less than the big boy articulated locomotives Union Pacific had retired. The difference was power delivery. Turbines generated continuous maximum torque that resonated through bridge members in ways that diesel consists dampened through their mechanical inefficiency. Anderson's maintenance budget projections revealed the financial reality that enthusiasm couldn't overcome. Operating 50 turbine locomotives across Union Pacific's system would require $4.7 million in annual track reinforcement beyond normal maintenance expenditures. Bridge structures needed $2.3 million in strengthening modifications to handle turbine service safely. The rail replacement schedule accelerated from 12-year cycles to 7-year programs, adding $890,000 annually to track department costs. The fuel consumption numbers complicated economic analysis further. Turbine 50 consumed 240 gallons of bunker C residual fuel per hour under maximum power operation. Diesel consists pulling equivalent trains using 185 gallons of refined diesel fuel hourly. The turbine ran on cheaper fuel. Bunker C cost 8 cents per gallon versus 18 cents for diesel. But the volume difference eroded savings. Fuel cost per ton-mile measured $6.04 for turbine operation compared to $6.01 for diesel consists. The operational advantages were undeniable. Single turbine locomotives simplified crew scheduling, reduced mechanical failures, and increased freight velocity that improved customer service. But the infrastructure costs and fuel consumption created a mathematical paradox. The turbine worked too well, generating so much power that Union Pacific's physical plant couldn't handle sustained operation without expensive modifications that negated the economic benefits that justified turbine development. Locomotive 50 proved that gas turbines could revolutionize railroading. Union Pacific's accountants were proving that revolution cost more than the company could afford. September 1952. Union Pacific's board meeting in Omaha turned contentious as directors reviewed 8 months of turbine operation data that created the most difficult decision in the railroad's 90-year history. Chairman Arthur Stoddard faced engineering success that threatened financial stability. General Electric had delivered on every technical promise. Turbine 50 accumulated 47,000 miles without major mechanical failure, achieved 98% availability compared to Wurcent for diesel consists, and demonstrated power capability that allowed single-unit operation where 3 diesels struggled. Crew reports praised the turbine's smooth operation, reduced vibration, and reliable performance across temperature extremes that degraded diesel efficiency. Customer satisfaction metrics showed dramatic improvement. Freight velocity on the Cheyenne to Laramie corridor increased 23% as turbine locomotives maintained schedules that diesel consists missed due to mechanical limitations. Produce shippers reported reduced spoilage losses from faster transit times. Manufacturing companies received raw materials 2 days earlier than diesel schedules provided. The operational benefits justified every optimistic projection about turbine technology. The financial analysis told a different story. Union Pacific's engineering department had calculated the costs of fleet-wide turbine conversion. Purchasing 50 turbine locomotives to replace 150 diesel units would require $17.5 million in capital expenditure. Infrastructure modifications to handle turbine operation added $23 million for track strengthening, bridge reinforcement, and yard facility modifications. The total $40.5 million investment exceeded Union Pacific's annual profit by $8 million. Fuel costs created ongoing concerns that quarterly accounting couldn't ignore. Despite Bunker C's lower price per gallon, turbine operation consumed 29% more fuel by volume than diesel consists of equivalent trains. The annual fuel budget would increase by $3.4 million across system-wide turbine deployment. Union Pacific's fuel purchasing contracts would require renegotiation with suppliers who currently provided diesel fuel volumes that turbine operation wouldn't need. Maintenance department projections added complexity to cost analysis. Turbine locomotives required 6% less scheduled maintenance than diesel units, generating significant labor cost savings. But the specialized tooling, training programs, and parts inventory needed for turbine service demanded $2.1 million in shop modifications. Union Pacific's mechanical forces understood diesel technology thoroughly. Turbine maintenance required skills that didn't exist in railroad service departments. The Interstate Commerce Commission complicated decision-making through regulatory authority over railroad rate structures. Union Pacific couldn't simply raise freight rates to cover turbine operation costs without ICC approval, a process that took years and faced opposition from shipper advocacy groups. The railroad needed to justify turbine conversion through improved efficiency that ICC commissioners would accept as a reasonable basis for rate increases. Competitive pressure from other Western railroads added urgency to the decision. Southern Pacific and Santa Fe were watching Union Pacific's turbine experiments closely. If turbines proved economically viable, competitors would adopt the technology, forcing Union Pacific into expensive catch-up programs. If turbines failed financially, Union Pacific would waste resources on experimental equipment while competitors invested in proven diesel improvements. Stoddard faced the paradox that would define Union Pacific's technological future. The turbine locomotive was the most capable machine ever built for mountain railroading. It was also the most expensive solution to a problem that diesel technology could solve adequately through less revolutionary means. December 1954. The crisis Stoddard feared materialized when Turbine 50 suffered catastrophic turbine wheel failure at Green River, Wyoming, forcing Union Pacific to confront the technological limits that enthusiastic early operation had concealed. Engineer Robert Jamison was pulling 83 loaded coal cars eastbound when the turbine's high-pressure stage disintegrated at 18,500 RPM, sending turbine blades through the engine casing in an explosion that sounded like artillery fire. Jamison executed emergency shutdown procedures that prevented fire, but the locomotive became a 470,000-pound obstruction on Union Pacific's primary coal route. The wreckage blocked mainline traffic for 11 hours while heavy equipment cleared the disabled turbine. GE's failure analysis revealed metallurgical problems that military jet engine experience hadn't predicted. Railroad turbines operated continuously at maximum power for hours, duty cycles that military aircraft never encountered. The sustained thermal stress caused metal fatigue in turbine blades that aviation service intervals prevented through frequent engine replacement. Union Pacific couldn't swap turbine engines every 500 hours like Air Force maintenance procedures required. The repair costs shocked management. Rebuilding the destroyed turbine section required $47,000 in parts and specialized machining that took 6 weeks to complete. Equivalent diesel engine overhaul cost $8,500 and finished in 8 days using standard railroad shop equipment. The turbine's mechanical simplicity advantage disappeared when component failures required manufacturer intervention that local shops couldn't provide. Anderson's maintenance department compiled reliability statistics that contradicted early operational success. Turbine locomotives averaged 11,400 miles between mechanical failures during the first year of service. By the second year, the interval dropped to 6,800 miles as thermal cycling degraded components. Diesel consists average 14,200 miles between failures with improving reliability as maintenance forces gained experience. Fuel costs accelerated beyond initial projections as Union Pacific expanded turbine operations. By 1954, the railroad operated 8 turbines, locomotives consuming 2.1 million gallons of bunker C annually. The volume created supply problems that diesel operation never encountered. Bunker C required heated storage tanks and specialized handling equipment that added infrastructure costs at every fueling location. Winter operations revealed that Bunker C's high viscosity created starting problems below 20 degrees Celsius that diesel fuel avoided. The coup de grace came through accounting analysis that measured total operational costs rather than individual advantages. Union Pacific's comptroller calculated that turbine locomotives cost $1.83 per mile to operate, including fuel, maintenance, infrastructure wear, and capital amortization. Diesel consists of equivalent service cost $1.47 per mile, despite requiring 3 units. The turbine's superior power couldn't overcome the cumulative economic penalties. Stoddard convened executive committee meetings that reached the inevitable conclusion. Union Pacific would continue turbine development with GE to solve the technical problems, but fleet-wide conversion was canceled. The railroad would order 50 additional diesel locomotives from Electromotive Division using conventional technology that matched infrastructure capabilities and maintenance expertise. The experimental turbine that worked too well had proven that revolutionary technology needed more than superior performance. It needed economic viability that Union Pacific's financial reality couldn't support. The turbine story didn't end with Union Pacific's decision to limit deployment. What followed revealed that management's fear was both justified and short-sighted in ways that shaped American railroading for decades. General Electric continued turbine development, producing second- and third-generation designs that addressed the metallurgical failures and operational costs that had defeated the original units. By 1958, Union Pacific operated 30 turbine locomotives, not the 50-unit fleet that full conversion required, but enough to prove the technology's niche advantages on specific routes where their power capabilities justified higher operating costs. The Sherman Hill corridor became turbine territory where the locomotives operated profitably despite their economic limitations. On 2% grades with 5,000-ton coal trains, a single turbine outperformed 4 diesel units in schedule reliability and crew efficiency. Union Pacific's operations department assigned turbines exclusively to mountain districts where their power advantages overcame fuel consumption penalties. The infrastructure modifications that management feared became reality through gradual implementation rather than catastrophic expense. Union Pacific strengthened rail on turbine routes using heavier 140-pound sections that improved durability for all locomotive types. Bridge reinforcements extended structure life beyond what steam-era engineering had provided. The investments benefited the entire railroad system rather than supporting turbines alone. Fuel technology evolved in ways that turbine skeptics hadn't anticipated. Petroleum refineries developed improved residual fuels with better cold weather properties and lower sulfur content that reduced engine wear. By 1960, bunker C prices fell relative to diesel fuel as refineries maximized gasoline production for automobile markets, making turbine operation economically competitive with diesel consists on heavy-grade service. The reliability problems that destroyed Turbine 50 at Green River yielded to metallurgical innovation. Union Pacific's partnership with GE produced turbine blade alloys that withstood continuous high-temperature operation for 50,000 miles between overhauls. The improved engines matched diesel reliability while maintaining the power advantages that made turbines valuable on mountain grades. By 1970, Union Pacific's turbine fleet peaked at 55 locomotives, the largest gas turbine operation in railroad history. The machines hauled 4% of the coal traffic that funded Union Pacific's expansion during America's energy boom. The turbines that management had feared became profit centers on routes where diesel technology couldn't match their capabilities. The ultimate irony emerged when diesel technology caught up through turbocharging innovations that Union Pacific's turbine experience had accelerated. Modern 3,600 horsepower diesel-electric locomotives combine turbine-like power with diesel fuel economy, making gas turbines obsolete by 1975. Union Pacific retired its last turbine in 1969, ending the 17-year experiment that had proven both management's caution and operational department's enthusiasm were simultaneously correct. The turbine locomotives that scared management by working too well had forced American railroading to evolve beyond conventional limitations. They proved that revolutionary technology didn't need to dominate entire industries to succeed. It needed to find the specific applications where superior performance justified higher costs. The question wasn't whether turbines were better than diesels. The question was where turbine advantages mattered enough to overcome their economic disadvantages. Union Pacific had answered that question by operating turbines long enough to make diesel manufacturers build better engines.